Okay, welcome. Oh, I see there's still some notes here from a previous. What is one of your lectures here? Was it a lecture of yours? No, nothing. Okay. Um, well, I think what could be nice is to start now with this repetition or recap. I have given you I've uploaded you some slides. There were some general or not so general questions to the topics we have covered this far. And maybe we can work through them together and see what you have found out also. Now I have to just pull them up. And where are they? Oops, just a second. Ah, okay. Let's have some recap on what we have done this far, and maybe we can um, work maybe in groups, and maybe you can help me, and we can look at one question after the other, and you tell me what you think should go in there. So, what are the fundamental properties of charges? Can you name a few of them? Well, actually, at least three. May, maybe we can do it table-wise. One table after the other is pitching in for an answer, or somebody is answering. Sorry? Yeah, that's good. It is positive or negative. That's one. Okay, that's one charge. One property of the charge. Give me another one. Sorry? It depends on the location. Yeah, well, that would refer to the force on the charge, but not the charge itself yet. Yeah, but yeah, it's a good point. Yeah, but it's not what I'm looking here now. What can you say about positive and negative charges? Uh, okay, the attraction or the repel, and which ones? Yeah, okay, that's like charges repel, unlike attract. And what else can you say about charges? I mean, if you think about how large is such a charge? Hmm? Sorry? Yeah, it's quantized. Yeah, quantized. That's the correct answer. Charge is quantized. So we have elementary charge, and whatever charge you have is always um, a multiple of this elementary charge. Thank you. We have the elementary charge. What is the unit of charge? Yeah. We have one C, that is Coulomb. Then, okay, do two negative charges repel or attract? I think we answered that. Yeah, so two negative charges, they repel, not attract. And uh, oh, that's Windows. It brings up. What? How does it come? Man, I don't want that. Okay, thanks God, it's gone. Okay. Oh, somebody just was talking about the uh, the action between the charges. So that brings us to this question: what is a force termed which describes this repelling or attraction of these charges? Don't hesitate. What force are we talking about? Hmm? Yeah, and we have a that is good, yeah, and we have also um, uh, another name for the law, basically, that describes this force. Yeah, electromagnetic is also good. I'm looking for Coulomb force, the Coulomb force. Okay, can you um, give the equation for that force? So it is the force acting on charge two due to charge 1 is F2 1, and it is opposed to the other charge, to the other force that is acting on the charge 1 due to charge 2. So now you probably have seen it so often now, you probably know it by heart. What is the equation? Yes, 1 over 4 pi epsilon naught times, sorry? Yeah, you're, I think I heard you correct. It's Q1 times Q2, and then in order, it is inverse proportional to the square of the distance vector. So that gives us a R2 minus R1. That would give us a square first, but then we want to also have the direction. So we have to give also the distance vector itself. And this gives us the direction, but it also gives us, of course, some contribution due to the magnitude, and that we want to get rid of again. So we write this here for getting direction, and we write it once more in the denominator as absolute value to normalize our direction vector. So that gives us this here. So it is the magnitude of the force is inverse proportional to 1 over the square of the distance vector. So what does it imply? The force between two point charges, how is it changing for larger distances? Is it becoming smaller or larger? Smaller. And what about if the magnitudes of Q1 respectively Q2 are getting smaller? Yeah, then it is also getting smaller. And also with respect to orientation of the force vector, what does it align with? I've added here already, it's parallel to something. What is it aligning with? Parallel to what quantity or what? Yeah, that's correct. The distance vector. Thank you. So in the distance vector, that is basically R2 minus R1. Sorry, this is just meant to be a regular bracket, not that you mistake it with a. Okay. Now we want to generalize it to the case where we have multiple charges. And okay, we can do that. You remember the formula. We just have written down the formula for a pair of charges. Now, if we have a multitude of charges, then this is a charge we want to have the interaction that is Q, and due to all the other charges which are Q sub I, and I is running from 1 to n. So based on, why can we do that actually? Why can we do, we had the Coulomb law and it was actually initially only for two laws and for two charges. Now we go here and add up all these charges. What is the reason for that? Anybody? Hmm? Yeah, because you can add the forces linearly. This is a linear law, so you can add them up, and the underlying principle is called the superposition principle. So superposition principle applies. This is a very neat thing for us. Okay, now give me the definition of the electric field as a formula. It's quite compact. Hmm? So how would you get the electric field? The definition. Yes, yes, exactly. So the electric field is the force divided by the charge. This is basically the definition here of the electric field. Unit? Unit of the electric field? Well, the unit is volt per meter. But you can also get through that, you can write force is Newton and the charge is ampere second. You also, if you convert it accordingly, you know, Newton, you can multiply it with Newton meter, then you have Newton meter is the work that is the same as watt times second, that watt is volt ampere second. So you can substitute that just like we did earlier, and then you have watt ampere second per ampere second. The ampere second is going out, then you uh, end up with the volt per meter. So you expand it with meter in the nominator and denominator. So what do the field lines of the electric field indicate? Well, the electric field lines in the end indicate the direction in which the positive charge is moving. And the more dense, the stronger the electric field. But of course, basically, that is the visualization we have chosen for the electric field lines, though the density as we plot them corresponds to the strength of the electric field. So it moves in this direction if you put it in the electric field, and if you don't fix it in any way, then I mean that's where the force will be acting, and this is the direction which it will push or pull the charge. Also, the way we plot it, that means the more dense, the stronger the electric field. So how does the monopole field look that is generated by a charge Q, which is smaller than 0? So smaller means it is basically a negative charge. So we have a negative charge here. And that means the field lines, they point towards the negative electric charge. And what we have in addition is uh, oh, what happened? Okay, these circles. Oh, come on. I think I should draw it by hand. Maybe this is not. Okay, enough. So we have here concentric, perfect circular lines, which unfortunately my tool here is a bit rejecting me to plot. But please, these lines should be nice and concentric, and that's not perfectly given. But what you have to notice is that these lines here in these green lines, these circular lines, these are basically lines where our potential is uniform. This is our electric potential here, the green one. And so the red lines are the electric field, and the green are the equipotential lines. And important, these lines here, they are perpendicular always to the field lines. So this is something, if you make a field plot, you have to make sure that the electric field lines and the lines of equal potential, they always intersect at a right angle. So what happens if you have now two opposite charges? Well, the field lines, we said they point away from the positive charge and they point to the negative charge. So, and that means at the monopole they'll go radial outward, but at the if you have these two charges, then this is how the field plot will look like. If you go out here, and then we can also plot the lines of equipotential. So these are our E field. And now we take also our potential. This looks like that. So what are the things you have to be careful of when you draw something? There's also actually a field line going out like that. And there's one coming in like that. So again, what did we say about the intersection of equipotential lines and the field lines? At what angle do they intersect? Anyone shout in? How many degrees? 90. Yeah, perfect. So 90 degrees. 90 degrees. Make sure when you draw that you look for that. 90 degrees, no matter where. Also, what you observe is that here in the center here, you will see here the field lines are a bit closer. And then as you go out, the spacing goes further apart. That is because the strength of the electric field is decaying here there by magnitude. And if you look at the equipotential lines, if you have here two charges, they are all well, you see they are pushed here. They're not actually not perfect circular, and they're pushed here a bit. You see here the spacing becomes closer, and outside it becomes further apart. So if you want the perfect solution, I mean, this is qualitatively, then you have to solve for the Poisson equation, but we will get to that equation later. Now we have a different case, and that is a case where two like charges, in this case, two positive charges, are brought together. And also, we said at the monopole, the lines go out. Also here they go out, but they bend here. Actually, this is. And you will also get equipotential lines again, which will roughly look like that. I will sometime give you, actually, they're coming up in the lecture slides. You will see the accurate plots, and eventually you get something like that here, and that becomes then increasingly. So this is also here you have to see that intersection will be always at a right angle everywhere. And of course, this is symmetric here. I have to apologize. This drawing is very rough. So this is the kind of field lines you see if you have two charges, two like charges in this case, positive, otherwise just the arrow orientation will be reversed, and the equipotential lines. And what happens actually if you have a charge right here, may it be some test charge, positive or negative, what kind of force is acting here? If you have it perfectly centered between these two charges. Anyone? No? Hmm? So these two charges, they repel each other, but they are fixed now. This is, I assume these two charges here, I have fixed them. So they repel each other, but they can't move away. Now I take a third charge, a test charge, that can move, and I put it right in the center here. And it could be a positive or it could be a negative charge. It moves up. I mean, if you look, what is the field here in the very center here? Because I mean, actually, the plot is it's very coarse, and actually, it looks like there's this information could be also missing. But if you look here, um, how is it likely? You know, these field lines, they bend out here and here also. If you have here a further line here, then it will also bend down here. This other one will bend down and here. And actually in this very center, you will not have any field line going in there. So what does it imply for any charge that you put in there? Hmm? Yeah, so actually if you put this charge in the very center, then you have, no matter if you have a negative or a positive charge, the forces from these two charges will basically balance out each other. And the charge is not experiencing any force. It will stay, you might think it will stay put, but the problem is you are in if you position it perfectly there, then there will be no force acting and it should be ideally be stay put there. But as soon as it tips out of this perfect spot, that balance is not applicable anymore. So it is basically in an unstable position. As soon as it tips out just slightly, then it will be experience some force or the other. And only in the very ideal case that you can position it and that you position it perfectly, then it will stay there. But as soon as it just jiggles a little bit, then it will, it's not a stable position here. So then, okay, here it says, with the knowledge of the lecture, draw the electric field inside a parallel plate capacitors. The plates are charged with the same amount of opposite charge. How does the electric field look at the edges of the plates? And that you have seen also in the lecture, we have field lines, they're going from plus to minus. And important, that field here is homogeneous. So as for the field lines, what does it mean? How do the field lines, how should they appear that you know that it's a homogeneous field? Hmm? Yeah. Sorry? Yeah, this is correct for the capacitor. You have it curved here, and also these here are not only straight; they're also spaced equally in equidistance. The spacing is because the spacing indicates also a variation of the strength. If the spacing stays constant, then the field also stays, the field strength stays constant. So you have here equally spaced field lines in that capacitor, in this parallel plate capacitors. So you have to make sure if you are drawing some field line sketch, to order to transmit the right information, the spacing really has to be uniform. And then out there, you can assume that also because it has to run from plus to minus. So I don't draw in everything here, but I will point to some important facts that you have to consider when you draw something like that. So I don't close these lines here. These are, of course, you have to consider also the lines never end in nowhere. When I have them ending here, then it's just because I don't know where to draw them anymore because they would extend quite far and it goes beyond my. But in general, you have to consider that a field line does not start or stop out of nothing. There has to be a charge, but it doesn't end like in nowhere. So if you plot something, your field lines begin at a charge and they end. It could be also some surface charge. Here in the capacitor, there will be then charges accumulated at the surface, and they provide the ending or beginning points for these field lines. So you never have a field line ending in nowhere. And if I do that, plot that here, then please keep in mind that this line is actually somewhere down there. It continues and closes here. So what you see at this parallel capacitor actually is that these field lines, they will come out also from the back side. But you see that here you have some fringe fields. We will return that to that. I mean, we haven't discussed that so much in detail, the capacitors, but I want to point this out to you already. So you have here fields that are extending out of these parallel plate capacitors, to these two parallel plates. And you see also that, however, as they do, the spacing here becomes increasingly large. That means the field becomes weak here. So in the end, if you have this parallel plate capacitor, the assumption usually is that these plates, the extension of the plates is also usually large compared also especially to their separation. And you have all the field concentrated pretty much between. That doesn't mean that you have not some field outside, but often you can say, I'm neglecting that field outside. And also that I will point out also later on, but maybe that I should point, I want to address already here. When you have these field lines and you assume these parallel plates, these are perfect conductors. So if you have a field line coming out of a perfect conductor or ending in a perfect conductor, it is always perpendicular also to that conductor. So I mean, we haven't specified that so much in detail here, but you usually can assume that these parallel plates are perfect conductors. This is usually an ideal assumption. So meaning also here your field lines, and also here you see this is not perfectly, but this here, they are all coming at a right angle out. And why is that? Just because a perfect conductor cannot support any tangential field component. So now we can also put in the equipotential lines. And actually, sorry, maybe I should plot that nicer, because actually you see the field is homogeneous here. They are all running parallel. We know the equipotential lines, they are also cutting at right angles. So the equipotential line is here a straight line. And it's a bit tricky. Draw that nicely with the plain hand on a tablet. So what you see also, of course, you know, the up and the bottom and top, it should be also be more symmetric. Of course, these are right and left symmetric, but as the field is getting weaker outside or very weak outside these parallel plate capacitors, also the spacing here becomes much larger of the equipotential lines outside the capacitor, and inside the spacing is closely and also uniform here. So now the question is, how do you generally, so that is the field for the two parallel plates. We will also then see how to compute the capacitance in such later down the lecture. So how do you generally calculate work in a force field such as electrical work? So in an electrostatic field, what is a general formula? What is work? What product do we need to take? Yes, force times distance or displacement. That means displacement maybe is, actually I like that better. Let's make displacement, or the displacement distance, yeah. That means, so if we have now some arbitrary path, then we get the, and we have some force field here. Then we integrate for the work from point 1 to point 2. And doing so, we actually can split up our, we can calculate the work basically by summing up the small contributions for the small delta omega, delta wi, and that is the force at the respective position r sub I, and always with the incremental delta r I. So basically you have here delta r1, another delta r, and well, actually they should be one adjacent to the other, but of course the point, that depends on how big you make the segment. You can have the first segment till here, between this point and this point. This makes your first segment, second segment here. And yeah, so you make that in a discrete fashion, or even better, you make that with infinitesimal small segments, and then you just end up at a curve integral, which integrates the force vector as a function of r along the integration constant dr, and that gives you p1 to p2 for f of r. So, and how about what does it mean for a vector field if the integration path does not play a role for the calculation of the work? What do we call a vector field with that property? Well, yeah, the vector field is conservative then. Hmm? Hmm? Sorry? Yeah. Okay. Thank you. Okay, now we can, I have given you two problems also in that homework. Have you worked on those? One is where you actually are supposed to calculate the, well, you have 2-point charges here. They are located in a vacuum, so your epsilon is equal to epsilon naught. We will see also that you can also have different kind of epsilon in different materials, so that depends on the medium that you're looking at. And then we have charge Q1, which is located at the position R1. Also, this position is given here with R1 is equal to 1 times Ex plus 1 times Ey. Then we have a second charge that is Q2, and it is located at R2, and that is located at 2 times Ex plus 1 times Ey. And the charge Q1 is set to be plus Q, so small q, that may be, for example, the elementary charge now. And Q2 is set to the negative, to the opposite type of charge, but the same magnitude. And now the question is, calculate the electric field that is generated by the charges Q1 and Q2 by using the superposition problem principle. Okay, there's some further problems, but now let me get to the problem. Let's go to this problem, which is denoted as Q3 for question 3. And so what is our vector R? Well, we can give it in 3 components. In the general form, if we have a 3-dimensional space, sometimes, I mean, with this problem, actually, we could also work for 2 dimensions, and you'll see it will end up the same because we have no information about set, but let's keep it at a 3-dimensional problem. So it has an x component, it has a y component, and it has a z component. And we have seen that the electric field, and we denoted E1, as a function of R is 1 over 4 pi epsilon naught. And Q1 is basically the small q. It is R minus R1 cubed here, R minus R1. Yeah. So what is that if you look at the denominator? What is this R minus R1? Well, let's first look at this R, by the way. We have given here that in written as with the unit vectors. You can also give that in give the vector here in a give it as a in column form. Then you just enter here x, y, z, and before maybe let me first write here what R minus R1 is, or let me first give you R1 here. As it is given in the problem statement, so it is 1 Ex plus 1 times Ey, yeah, this is what it says. Then we can expand it. Ez is not given, but that would be 0 times Ez. Let's keep it a bit more general. You don't have it for that particular questions. You would not have to do that. But I would like to keep it in a bit more general form. So if there's also a set component, then you have it in here as well. So that, if you write it as a column vector, is 1, 1, 0. That is your R1 vector. Why is it? To change something in the setting so it doesn't switch off all the time. That is a bit not so nice if it switches off. Okay, so then what is R minus R1? Well, in the general form, because we have said R is X, Y, Z, and I would like to keep it right now general because that's what it is asked for. Give the electric field E as a function of X, Y, and Z, so that our R is X determined by X, Y, and Z. So R minus R1 is then basically X minus 1, Y minus 1, and 0. So that means our R minus R1 cubed is x minus 1, right? This is the x component here. We square it plus the y component, y minus 1, plus z squared, and to the power of 3 half. Our epsilon is, that is a, a bit rounded, but you can also say it is roughly, but usually that is a good value to calculate with. It's 8.85 times 10 to the minus 12. This is also a quantity that is good to know by heart. Also, please know by heart the units here. Now you can also check if the quantities are correct. That is always, if you solve for some problem, if you have put in the right formula, but I'm sure that's what you're doing anyway, is check whether the units are right. If the units do not add up to what you expect, then you probably have done some error in there. Yeah. Yeah. The point is that I want to get the norm of the vector or the magnitude of the vector. So that you do by taking the square of each component of the ex plus the square of the ey component plus the square of the ez component. Hmm? Sorry? Sorry? Yeah. Sorry, I think acoustically I didn't. So I want to get, so the power of 3 is because I just picked out this one here because this appears here then, right? Here. I want to get to know what's in the denominator here. So that's why I compute that to put that this is this part of the equation. Now, if you want to see make a sanity check concerning the units, what are the units? We have the unit of the electric field, and we see we have here the unit over 1 over the unit of epsilon naught. Sorry. And we have here the unit of charge. This is ampere seconds. We have here 1 over r squared in the effectively. So that is basically we have a square meter. So what is this? The epsilon, what is the unit of that is farad per meter. We haven't, I think, really mentioned this, but that will come also. Farad is basically the unit of the capacitance, or what we have, however, given is it has a unit ampere seconds per voltmeter, right? So let's insert that here. That means here in the first part, we have here voltmeter per ampere seconds times ampere seconds per meter square. So this crosses out. You have 1 meter that falls out, and then just sanity check. You see the formula, you add all the units. So that's always good to carry along also the units. Then you see if you have done some mistake, then the equation also doesn't yield the right units. So also important, if you give any calculations, you always have to give units. Never forget about that. So we have now we have computed here E1. This term for 1 over R So this you insert in here, and your contribution from the second charge to the electric field is to the second contribution to the electric field from the second charge is E2. It's also a function of R, and it is again 1 over 4 pi epsilon naught. The charge this time is minus Q, and it is R minus R2 here, what we have in the denominator, to the power of 3 times R minus R2. Yeah? And this time we have R2 is 2 times EX plus 1 time EY. That gives us a vector 2, 1. Sorry, actually, we said we want to carry along the set also. It is 0 times EZ. And that would be a 2, 1, 0 if we write it as a column vector. So that means the R minus R2 is then, if you, it is X minus 2 times EX plus Y minus 1 EY plus 0 times EZ. So, and the question here was calculate the electric field. That is basically our total field. I call it E total, is E1 plus E2. And you see, we have seen that before, the superposition principle, as it is applied to the Coulomb force or also to the electric field. And means let's add up these two contributions. We have 1 over 4 pi epsilon naught. And we have here, this was Q1. I keep it to get more general, but I'll switch back in a moment. That is R minus R1 to the power of 3 times R minus R1 minus, sorry, plus, the second one is Q2, and this is R minus R2 to the power of 3 R minus R2. You agree? So we had said Q1 is Q, Q2 is minus Q. So let's put that in again. Then we get the E total is, we can pull out the Q, 4 pi over epsilon naught, 1 over R minus R1, the power of 3 R minus R1. And now let's, for example, plot, no, let's not plot, but let's get the value. What example, what is, we set R here to 0, 0, 0. That means we are at the origin. Then our field at 0, 0, 0. But you can put in an arbitrary coordinate now. You insert. So what do you get? Here you see x, y, and z are all 0. So you have here minus 1 squared, minus 1 squared plus minus 1 squared plus 0. So it gives you, so it gives you 1 over square root of 2 to the power of 3. Oh, sorry, that is a plus, right? What do we have? No, that's all minuses. No, sorry, the position is 1 and 1. Yeah, that's right. And you insert that also in the second. You agree to that, or do you? So we have set here x, y, and z to 0 here. And we have done the same thing here for R2. And so you get the total field here. What is this? Okay. Okay, that is answering question Q3 here in the problem. And now, um, maybe have you, because since you have looked at it also, have you calculated here the force between two charged particles? Hmm? Sorry? Ah, okay, then good, then let's do it together. So problem one here, force between two charged particles. Anybody has a solution already for it? No? Okay. Well, actually, what is the question posed? This is a proton, and the charge is Q, which is plus E, so it's plus the elementary charge. And an electron, not surprising, also the charge Q is then minus E, that is the electron charge of a neutral hydrogen atom, are located at a distance of the so-called Bohr's radius. That's A naught, and it's 0.529 times 10 to the minus 10 meters. Now the question is, or the task is, calculate the magnitude of the electrostatic force between those two charges. So you only need to get the magnitude. There's no direction asked for, and also not the information. That is not relevant. Please use the following constants. So we have the elementary charge. It is 1.602 times 10 to the minus 19 Coulomb. And we have the dielectric constant of vacuum, which is E naught, which is 8.85 times 10 to the minus 12 ampere second per voltmeter. So that's actually, we want to know what is the magnitude of the force. And we get that from Coulomb's law. It is 1 over 4 pi epsilon naught. And the charges is E and minus E. Okay, we are looking for the magnitude, so we can drop that sign here. It's E squared. And then we have here the separation of these two charges. We can also reduce it here with the square, and we don't need to determine the direction. So then we just have to insert actually all of that. We have 1 over 4 pi. Our epsilon here is 8 to the 0.85 times 10 to the minus 12 ampere second per voltmeter. And the whole thing is then multiplied by the elementary charge squared. This is 1.602 times 10 to the minus 19 squared. What are the units? It's also ampere seconds squared. And what is the radius? That, I mean, the distance vector, or the separation in the end, that's the Bohr radius. It is the 0.529 times 10 to the minus 10. Also, the radius enters here with a square, meter squared. So that is 1 times 1 over 4 pi, 8.85. Now let me get these exponential terms to the back. We have on the top line here 1.602 to the power of 2. And we have the 10 minus 19 squared. That gives us a 10 minus 38. And we have at the bottom still the Bohr radius. It is 0.529 squared. And we have here on the one hand the 10 to the minus 12 and the 10 to the minus 10 squared. 10 to the minus 10 makes minus 20, and then times minus 12. That gives us 10 times 10 to the minus 32. Yeah. What happens to the units? We have here the voltmeter, ampere second. That is from the epsilon naught. Then from the charge here, we have here ampere second squared. And from the radius, we have meter squared. So let's simplify that. 1 ampere second goes out. 1 meter goes out. And now 10 to the minus 38 divided by 10 to the minus 32. There stays a 10 to the minus 6. And the remaining parts, I suggest you enter best in your calculator. So this roughly gives you 0.08246 and so on times 10 to